The guy who was arguing with you on the start time didn't show, huh? All right. So we are recording. Let's get the PowerPoint up here and from current slide. Okay, here we go. Any questions on anything first? All right. Book situated here. All right, we're on example 7, bottom of page 351. Okay, and get the pen out. It says rewrite this expression 1 plus 1 plus sine over 1 plus sine x so that it is not in fractional form. In other words, get rid of the denominator. Okay, so how do we do that? What would be your first step?
Did you multiply 1 plus sine x?
1 minus sine x. Okay? Multiply by its conjugate. That's always a pretty safe thing to do. And I think as soon as we do that, you'll see why it's a fairly safe thing to do. Let me get my pen set up. Okay, so we got 1 over 1 plus sine x, okay, and multiply by its conjugate, 1 minus sine x, okay. So if you multiply the denominator by that, you better multiply the numerator as well, 1 minus sine x, right? So I can do the numerator, it's 1 minus sine x. You tell me what the denominator is now. Are actually 1 minus sine squared, right? 1 minus sine squared x. I mean, FOIL it if you need to. 1 times 1 is 1. Okay, got it. Then you get a minus sine x, a plus sine x, that adds a 0, and then minus sine squared x, right? Now, do you see why that was a pretty good choice to do? What is 1 minus sine squared? That is cosine squared x, okay? So this would be 1 minus sine x over cosine squared x, okay? Well, we still have it in fractional form, but what is cosine squared x? 1 over cosine squared x.
Secant.
Yeah, that's secant squared x. So then you could write this as 1 minus sine x, I can't write, okay, times, it doesn't matter which side you put it on, I think I put it on here. I still can't write secant squared x, okay? You got rid of that denominator, okay? Now that may not be the only way to do it, but that certainly was one way. Ooh, got too much. Okay, let's see. Okay, so that was one way. Here's the other way they suggest doing it. Going back to this form here, that certainly gets rid of your denominator. It's not in fractional form. Here's the other way they said, let's do it as 1 over cosine squared x minus sine x over cosine squared x, okay? And 1 over cosine squared x is, just like before, secant squared x minus, now this could be written as, just this part here, as sine x over cosine x times 1 over cosine x. What's sine over cosine? Tangent x. And 1 over its cosine? Secant x. Okay? Now, from that, if you wanted to take it one more step, which I'm not sure they do, you could factor out a secant x and leave it secant x. Don't do that one, okay. Secant x minus tangent x. Okay. So lots of ways you can leave your answer. This did exactly what they asked for. This does exactly what they asked for. That does exactly what they asked for. As long as you don't have such an ugly looking C there. And now I don't have any C there. Okay. So, they left it the middle way, the one right there. Okay. Now, that's, again, my little soapbox here. My big gripe with WebAssign, which is the online homework package that comes with the book, they're going to look for one and only one answer. These are correct, but only one of them's going. They'll say the others are wrong. Okay, and they're not wrong. They are absolutely correct because there's many ways sometimes to express answers. Okay, there is a checkpoint there. Well worth your effort to do that as well. All right. Now, let's see how they did it. Sorry, I forgot this. This is one they are doing. So what they do from the Pythagorean identity, boy, they take you around the mountain to do this. Well, I guess they had to give you some rationale for doing what I said. But if you ever have either a 1 plus sine, 1 plus cosine, sine plus 1, or cosine plus 1, 1 minus cosine, 1 minus sine, or even a sine minus cosine 1 or a cosine minus 1, you can factor out a minus 1 there. Those forms lend themselves to be multiplied by the conjugate, then you get something you can, using a Pythagorean identity. So I told you to do it first, but they're showing you why you did it, not that you would have ever started. Let's see what cosine squared x is, okay? That's 1 minus sine squared x. That factors is this, and that's part of this one, so why not multiply by that? But if you multiply by that, you must multiply the numerator by the same thing, okay? All right. So once you do that, you get 1 minus sine x over 1 minus sine squared x, which we know is cosine squared x. Now this is where we parted ways in how we were approaching it. They split that into two fractions, which is a very good technique to do. But I thought, why even mess with that? Just say that's secant squared, and be done with the problem. But no, they did split it into two parts, which is fine, perfectly correct. And that becomes a secant squared minus, they leave it as 1 over cosine squared. And then split the sine over cosine squared as sine over cosine times 1 over cosine, which then they ultimately produce to be secant squared x minus tangent x times secant x. Okay? Perfectly good form there, too. But the other two are as correct. Whoa! And that's the last slide, but there's two more examples. So let's do example 8. Now, are you comfortable temperature-wise? Yeah. To me, it's a little warm, okay? But yesterday, my first class met down in 205 because it was too big for this room. It was freezing in that room. I came down here and it was balmy, okay? In fact, almost too warm. And now it feels almost too warm, too. But anyway, let's do example 8. But this hot, dry air always clogs up my head. So, okay. Now, they tell you the substitution to use, so we'll let them get by with it. They say, use this substitution, x equal to tangent x, right? Yeah, tangent theta, sorry. Now, can theta take on any value in the world?
No.
Why not?
Count whenever tangent, cosine is equal to 0.
Right, and where does that happen?
At
At all your half pi's. Okay, absolutely correct. So we have to restrict the domain of that theta, and they restrict it even further than just negative pi halves to pi halves. They go 0 to pi halves, and there must be a reason for that too. Maybe we'll see. 0, and they say less than, though it could be less than or equal to, I think, theta, but it has to be less than pi halves. You can't have the equal sign there because that's not defined there. Okay? And it says to write this expression, okay, the square root of 4 plus x squared, okay, as a trigonometric function of theta, as a function of theta rather than x, okay? So, they tell you the substitution to make. There's your x over there. So if x is 2 tangent theta, over there is in an x squared form. So what is x squared? It would be what?
2 tangent squared.
Yeah? 4 tangent squared theta. Okay? Because you square both the number and the trig function. Okay, well, let's then take it another step and do a 4 plus x squared. That would be, just add 4 to both sides, right? 4 plus 4 tangent squared theta, right? Now let's take the square root of that. Okay? Now, what do you notice you can do to that expression under the right-hand square root? Ugly expression, by the way.
You take away the square root, or the square.
Outside.
Square root.
Oh, okay. You think that's a perfect square?
Oh, it's not.
It's not. Okay. So I don't know how to do that. Now I can do it in pieces. What's your F word? Have I told you all that one? Maybe not. Okay, sorry.
Factor.
Factor, exactly. Let's factor first. Okay? That would be the square root of, what can you factor out of that?
A 4.
A 4. What are you left with? 1 plus tangent squared theta. Okay. Now, I know that 4 is a perfect square. What's it a perfect square of? 2. So that part we can pull out. That's going to be 2 times the square root of. But what is 1 plus tangent squared theta?
It will be some type of identity.
All right, good. Okay. That leaves narrows it down quite a bit, doesn't it? Okay, what identity would that be?
Secant squared.
Secant squared theta. Excellent. Okay. Secant squared theta. Okay. Now, what would that be? Square root of secant squared is? Secant theta. All right. Now, I think we kind of get a glimpse of why they limited this to only positive values of theta. Because a negative, let's see, what would be the situation there? A negative theta would produce a value. When you take the positive square root of it, it would still come up positive. So just to eliminate all that, we'll just take theta being positive, so everything here is positive, and your answer is 2 secant theta. Okay? I think otherwise you might have to, you don't have to put after the you have two possibilities. So let's just leave it. See how that works? That is now a function of theta. All right. Now, why did they show us that? You're going to continue into calculus, right? Okay. When you get to Cal 2, you will be doing some trig substitutions to help solve integrals that have forms like that in it that there's no way to solve in that state. But if you do a trig substitution, yeah, you can do that. Okay. So that's why they showed you that without telling you why you showed you that. Okay, now, and most of the time in the calculus applications of it, we will also draw a little triangle. Okay? And it's taken from this substitution right there. If x is equal to 2 tangent theta, that means tangent theta is equal to what? X. How do you isolate the tangent theta?
X over 2.
X over 2. But how do we define tangent? Any old tangent.
Sine over cosine.
Okay, but let's do it in our old hens.
The opposite over adjacent.
Absolutely. So therefore you can draw your little right triangle here, okay, and say this is your angle theta. The opposite side is x and the adjacent side is 2, right? Opposite over adjacent. What does that make your hypotenuse then?
It's 2 squared plus x squared.
Okay, so that would be 4 plus x squared. But that would be the square of the hypotenuse. So the hypotenuse would be the square root of 4 plus x squared, which is exactly this form right there. Hey, look at that. Okay? So, yeah. This is kind of all fits together pretty well, doesn't it? Okay? And then if you think about this, what is secant theta?
1 over cosine.
Okay, that's in the unit circle.
Secant would be hypotenuse over adjacent.
That's it. Hypotenuse over adjacent. There's your hypotenuse divided by adjacent. Multiply both sides of the derivative. 2 secant theta. Yeah, that's exactly the same right there. Okay? So, not obvious beforehand, but once you do it, it becomes pretty obvious in retrospect. Okay.
I noticed I had an integral by the trigonometrical substitution.
What's that again?
On my book, I had the integral by the problem.
Oh, really?
Well, it said whenever, for example, it said trigonometric substitution, and it had the integral by it.
See, I didn't make it up. Okay. All right. So exactly. Yeah, they don't have that in the text, but good for that. But at that top example, though, you see that little integral sign at the top? Does it have it there right by example 8? Trigonometric substitution?
Yeah.
Yeah. So that's indicating why they did that, okay, without telling you. But yours told you that. Okay, let's go down to example 9 and see if that works in any way similarly. May or may not. I don't recall that it does, but let's see. Ooh. Rewrite the log of absolute value cosecant theta plus the natural log of absolute value tangent theta is equal to the natural log of absolute value cosecant theta times cotangent theta. Times tangent. Is that right? Yeah. No, No. Sorry, I was looking at their solution. I was going to say that's solving this issue for you. Okay, sorry. My eyes lost track of where they were. Okay, it just says rewrite that as a single logarithm and simplify the result. Okay. Now, a couple things. Time out. Logs. What can they never be? What can you never take a log of? Zero. You're absolutely right. And what else? Negative number. You never take the log of 0 or a negative number.
That's why they have the absolute value bar.
That's why they have the absolute value bar set. Very good. Now, do you know sort of why that's true? The log is the...
I know it's like for the exponent.
Okay, you're absolutely right. It's the inverse function of the exponential function equation. Well, exponentials are either like this, if for positive numbers, like this for negative numbers. Okay? But guess what? They never reach 0, and they never are negative. So therefore, the inverse operation can't have, since that's not in the exponential function's range, it can't be in the log function's domain. Okay, so yeah, that's why the absolute value bars are there. Now, do you remember any of the rules about logarithms?
Last time we did them, I was in...
Say that again.
So last time I did them, I was in calculus.
Right.
I just remember the derivatives.
Okay, good. That was what?
Like 1 over u.
1 over the u, right, exactly. 1 over, this would be, derivative of that would be 1 over cosecant plus 1 over tangent, okay? And then you can play around with those. But we're not doing that now, okay? Wow. I'm surprised you didn't score higher than 113. But he almost just picked that and threw you in there, right?
Yeah, I just picked that. I didn't take the pretest.
Okay. You didn't happen to be in, what do they call it? Advanced placement calculus, were you?
I was in AP Cal last year.
You were?
Yeah.
Okay, did you take the exam at the end?
Yeah, I think I just made it 2 or 1.
Okay.
I didn't score very high.
Okay. So you didn't get to advanced placement. Okay, but it sounds like you remember it pretty well.
I did good in the class. I just forgot a bunch of this stuff on the test.
Right. Well, I'm teaching Cal 2 right now, and I'm having trouble reminding my students that derivative of a log is 1 over the thing. You know? So I wish you were in there. You could help them. You know. But, okay. But you'll be in it next term, right?
Yeah, I'll probably take that next semester.
Good.
And probably a physics class.
And what?
And a physics.
Yeah. Okay, wait. Wait. What's your major pre-engineering?
Yeah.
Which one? You may not have chosen yet, but just okay.
I know all of them will probably like at least the physics.
Yeah. Okay. Here's the deal, though. Most of the 4-year schools that have physics programs require you to do the engineering physics, which is the calculus-based physics, meaning you have to have Cal 1 before you can get into that.
Okay. I know there was like a physics with Cal 2.
Yeah. Okay, but it's physics with calculus 1 and 2. Okay, not with calculus 1 or calculus 2. Physics with calculus 1 and 2. That's the engineering physics. The what they call, I don't know, college physics or general physics, that's tree-based. And yeah, you could go into that next term, but if you're a pre-engineering major, I would wait until I had calculus and then do the calculus-based.
So just take it next year.
Yeah. Are you planning to come summer?
I don't think about it because I got full tuition, so I'm not sure if it covers summer classes.
Okay. Well, in the summer, we have bigger physics classes than we do fall and spring because transient students come in. So it never has failed to make in the summer in the last probably 15 years. So it's a good shot that it's going to make in the summer. This time was the first time in several years that we haven't had both of our physics made. We have to stack them fall and spring because we have so few students. So you would be in there with general physics students, but you could have. But we test them separately. They have different books and stuff. But physics is the same, and we use books by the same author, so they present it the same way. Even use a lot of the same PowerPoint, so it makes it fairly smooth. But in the summer, not every summer, but quite often we can split the sections because we have enough students to do it. Last summer was the first time in many years that we couldn't split it because we had either fewer than 10 in one or the other, so we had to keep them stacked. So Dr. Bryant taught us if we split them, I teach one of them. So anyway,
we got into physics and calculus last year.
What's that?
So we got into physics last year,
Yeah.
where we talked about like velocity and acceleration and all that.
Yeah. So that'll be pretty much all that to you too. All right, good deal. So you remember any of the other rules for logarithms? Remember how to differentiate it? Do you remember any of the arithmetic rules for logarithms? Why did good old John Napier come up with them in the first place? Okay. And this is sort of old technology. Have you ever even heard of what a slide rule is? Okay. A slide rule was what? It was sort of a precursor to the calculator. It's what you use for calculating pretty hefty numbers, and gave you an easier way to do it, okay? And what it was based on is you're dealing with, sort of like you said before, the exponents of things. And remember, when you're multiplying the same base with different exponents, what do you do with the exponents? Say x cubed times x fifth. X cubed times x to the fifth.
Oh, you add the...
You add the exponents, okay? Now, in a weird kind of twisted way, that's what logarithms are doing. When you are multiplying big numbers, if you take the log of each number, add the logs together, not multiply, but add, and then take the anti-log, or the exponential of your answer there, and you get the number you were looking for. That's really what a slide rule did. Slide rule was a device that looked sort of like a ruler, but it had a movable slide in the middle. So you would take one number, and everything was a log scale. So you would say 15 would be 1, 5. Now that would be in a log scale, that would be somewhere here, and multiply that by 225. So you find this, to slide this to here, take 225 here, 2.25 on the log scale, and get there, and then the answer you see there, you do the anti-log of it, in other words, do it in the reverse way, and you get the answer. And just read it off because it's already on the log scale. So with that now, we're doing this backwards. We have the sum of two logs. What does that yield?
If you would have the exponents you had.
Okay. So that would be sort of like what I just said. The log of a product is the sum of the logs. So the sum of the logs is the log of the product. Okay, so this would be the same as the ln of cosecant theta times tangent theta. Okay, now, in a sense, you can probably remove your absolute value bars or not. So let's just do ln of, and what is cosecant?
1 over
Sine. And you can leave that in absolute value bars. The 1 doesn't have to be there, but that is. And what's tangent? Sine over cosine. And you could leave the absolute value bars there if you wanted to. Okay? And the sines disappear, and you have the log of 1 over cosine. okay, which is the log of secant. Okay? Now, is that all they said to do? As a single logarithm and simplify the result. So, yep, that's what they wanted. Okay. Another way you could have done it, which actually comes out being the same thing, is because the log of a product is the sum of the logs, the log of a quotient is the difference of the logs. That would be the log of 1 minus the log of gradient cosine. Yeah. Okay. And what's the log of 1? 0. Okay. And so you have minus the log of cosine. That happens to be the same as log of secant. Okay. And here's why. Minus log of cosine. Okay. When you have a minus sign or anything in front of the log, you can pull that up and make it the exponent. So that's the log of cosine to the minus 1, which is exactly secant. So log of secant. So you're back where you started. They're the same thing. Completely equivalent. And again, so both of those answers would have been right. But Weberstein would have only recognized 1. Okay?
Cosine to the -1, would that not be secant?
That is secant. That's what I'm saying.
Okay.
Yeah. Cosine to the -1 is secant. So that's exactly the same answer. All right. There is a checkpoint there. Please do it. Now our most favorite vocabulary. Yay! All right. And what secant u over cosecant? Cosine u? No, I can't read. Sine u over cosine u? Tangent u. 1 over sine u? Cosecant u. 1 over tangent u? Cotangent u. Secant of pi halves minus u.
That'd be tangent.
Pi halves minus u is the
Cosine.
No, wait. It's the complement of u. So the secant of a complement is the CO. Complement, CO, that's where it came from. When we did these at first, you said, never heard of those.
Cosecant.
That's the cosecant u, okay? Sine squared u plus cosine squared u is 1 always, and sine of negative u is? Negative sine u. Perfect, because sine is an odd function. Strange bird, you know. Okay. Homework exercises here. Any of the odds, 7 through 11. They're all at Calc Chat. 7's at Calc View. Any of the odds, 13 to 17. They're all at Calc Chat. Either 19 or 21. They're both at Calc Chat. 19's also at Calc View. Any of the odds, 23 to 31. They're all at Calc Chat. 25's at Calc View. Any of the odds 33 to 39, they're all at Calc Chat. 35's at Calc View. 41's at Calc Chat. 43 or 45 are both at Calc Chat. 43's at Calc, 43 to any of 43 to 47, they're all at Calc Chat. 43's at Calc View. Do 49 is at Calc Chat. Do 51 is at Calc Chat. Either 53 or 55, they're both at Calc Chat. 53's at Calc View. 57's at Calc Chat, 59's at Calc Chat, either 61 or 63, they're both at Calc Chat, 61's at Calc View. There is a physics type problem, a friction problem on 65, which is a pretty good one to look at. It's at Calc Chat. The true false 67 at Calc Chat, it should be there anyway. And then analyzing trig function 69, you should be able to do that, and Calc Chat should be able to help you. I don't really care for 71 because it's written incorrectly, and it tells you that, but you're trying to figure out why it's incorrect. So I hate for them to write something down that's wrong. Okay, and then 73, you can look at that if you want to. I don't know if that's a Calc Chat or not. And 75 is a rewrite that you should be able to do, and probably is a Calc Chat. All right, any questions on those? All right. Let's go on to, let's see. I didn't bring my watch up, did I? So you'll have to keep me on target, right? Let's see. 9:38. We're going until 10:15, so we got plenty of time. Okay. That's not what I wanted to happen. But it happened. So I'm going to have to minimize this. Ah, there it is. I knew it had to be there somewhere. All right. Let's go from Screencast-O-Matic. Well, it's still running, so I didn't need to do that. Let's just do this from current slide. Good deal. All right. Chapter 5 is still analytic trigonometry. In other words, we're analyzing or using trig functions to simplify, solve whatever it needs to do. And 5.2 are verifying trigonometric identities. All right. What do we mean by an identity? Do you know?
I guess the form of the function.
Okay. Okay, in one sense, it's a form. Here's the key to it. It's always true. No matter what value you put in for the variable, whatever, it's always true. Okay? It looks just like an equation. It is an equation. But in equation, there's two types, and we're going to be verifying trigonometric identity since that's the title of the thing. And here's the introduction. Okay, so valuable slide. In this section, you will study techniques for verifying trigonometric identities. Now, here's what I was getting at. Most of our equations we play around with are what we call conditional equations. It's an equation that is true for only some of the values in the domain. You try to solve that equation to figure out what values would make that true. That's a conditional equation because it's not always true, only for certain values. For instance, sine of x equals 0. Is that always true? No, it's only true for
X equals for x, whatever value that x is.
For what?
For whatever value that x is.
What would x have to be to make that true? Think of your sine function. When is that equal to 0? At 0. At
0.
At 0.
1.
Pi. At pi.
0.
2 pi.
2 pi.
3 pi. 4 pi. Is at any n pi. But that's the only one. Pi half is not. Pi half is 1. Okay? So that's not true for any x, only certain x. That's a conditional equation. Only true for multiples of pi. Positive or negative multiples of pi. Okay? Integral multiple of pi for their integers. Okay? Where n is any integer, positive or negative. Okay? When you find those values, you're solving that equation. Okay? That's what you do with conditional equations. However, there is another type, the other hand, an equation that is true for all real values in the domain. That's called an identity. And that's what we've been dealing with already. They moved this around, but this is true for what values of x? Every stinking value of x you can find, that's going to be true. Cos sine squared plus cosine squared is always, always, always equal to 1. So that equation is an identity. True for all real numbers x. You can't solve it for any one because it's true for all. So what we're going to be doing in this section is playing around with some identities, okay? And basically verifying whether they're true or not. They're going to indicate they are, but we have to show that indeed they are. So that's what we call verifying trigonometric identities. Now, they say although there are some similarities, Verifying a trigonometric equation is an identity is quite different from solving an equation. Because in solving an equation, usually you're either trying to isolate something on one side, so you move things across the equal sign. Divide, multiply, add, subtract, square root. You do things across an equal sign. Okay? For an identity, we never cross the equal sign. We can play with this side, we can play with that side, but don't ever cross the equal sign. Okay? There's no well-defined set of rules to follow in verifying trigonometric identities, and it's best, it says, to learn by practice. So practice, okay? All right. Here's some of the guidelines of it. Now, these are the book's guidelines. I don't always go by these. It says work with one side of the equation at a time. It's often better to work with the more complicated side first. Okay? Now, I don't really go by that too much because as long as you don't cross the equal sign, you can do things to this and do things to this. They don't have to be related to each other as long as all the steps are true. So you don't have to do just one side or another. Just be sure you don't cross the equal sign. Okay? Now, just like in simplifying expressions, look for opportunities to factor. If you see them, factor. You might be able to do it. On one side or the other, add fractions. Okay? Square a binomial. You have to be careful when you're doing that. There's a reason for that. Because if you square something that's negative, you're going to make it positive only. Okay? Well, and square something that's positive, it's going to be positive only. So you can square two different things here and get the same thing when you square it, but they're not the same thing to begin with. You have to be careful when you square something like a binomial or something. But it's okay to do, just be careful with it. Okay, create monomial denominators. Whatever you do to simplify, as long as you're only doing it to one side or the other, that's a good thing to do. Okay? Look for opportunities to use the fundamental identities. Okay? Now, here's my approach on this. If you see the squares in there, think Pythagorean identities. Okay? If you don't see squares in there, try to get things in terms of sines and cosines. Okay? Note which functions are in the final expression you want to see, so you can look across the equal sign, just don't cross it. Look across it, but don't physically cross it. Okay? Sines and cosines pair up well. Secants and tangents pair up well, especially with Pythagorean. Cosecants and cotangents pair up well with Pythagorean. So keep those in mind if they're squares. If the preceding guidelines do not help, try converting all terms to sines and cosines. You know, I probably do it much faster than they do. I'll go to that pretty quickly. If I don't see anything that seems obvious, I usually try that. Now, the last statement here, always try something. Okay? Now, don't do something that's incorrect. I mean, don't make up a new identity that's not really an identity, but always try something. Because even in making an attempt that doesn't lead you anywhere, you might see, or it might prompt some idea and say, oh, but I could do this, couldn't I? You know, so it could give you more insight. All right, blah, blah, blah. Verifying trigonometric identities, useful process when you need to convert a trigonometric expression into a form that's more useful algebraically. That's what we usually are trying to do, solve equations, not identity. When you verify an identity, you cannot assume that the two sides are equal because you're trying to verify they're equal. So usually what I do, I put a question mark over that equal sign to remind myself, number one, don't cross it, but number two, we don't know that it's true, let's see if it is. As a result, when verifying identities, you cannot use operations such as adding the same quantity to both sides, that's what I've already said, or cross multiplication, or anything else like that, because there you're crossing the equal sign. Just don't do that. Okay. Here's one right here. Verify this identity. Number one, we don't know at all that it's true. Okay. Which side would you suggest we work with first?
Left side.
Left side, because that's the more complicated side. And the right-hand side's already in terms of sign. So can't do much to simplify that yet. We might see something later. All right. Now, there's a couple of things you could do. Okay? Let me get my pen set up. I know what they want us to do first. Okay? But now, let's go on and do it. When you see the squares, what should you think? Pythagorean identities. Okay? Now, secant squared minus 1, is that one of them?
That's tangent squared.
That is the same as tangent squared. So that would be tangent squared theta over secant squared theta. Now the question, is that equal to sine squared theta? Most of the time I don't write down this over and over, but just to show that I usually do put that question mark there. We don't know that's true. Now what would you think of doing on the left?
You can either change the denominator, but that's also a Pythagorean identity.
Okay. Yeah, and you could sort of go around in circles on that for a while. Now you got them in this form. Now my favorite issue is get everything in terms of sine and cosine. What is tangent squared in terms of sines and cosines?
Sine over cosine.
Sine squared theta over cosine squared theta over, and what's secant squared in terms of sines and cosines? 1 over, what you say?
1 over cosine.
Cosine squared theta. Perfect. And now what do you notice?
Could you cancel out the cosine?
Yes, you can. I usually don't like the word cancel out because people try to cancel out all sorts of things, but you multiply numerator and denominator, as long as you're on this side, you can do that, by cosine squared theta. And that will wipe them both out at the same time, which is like canceling them out. And what do you have? No, just sine. Sine squared over 1, which is just sine squared theta. Done. Did verify those are exactly the same forms. Now, here was another way to do this. This was my first inclination. And maybe it's what the book wanted to. I haven't looked to see what the book said. Here's what my first inclination was. Writing that as secant squared theta over secant squared theta minus 1 over secant squared theta. Is that not true? When you're adding fractional forms, you have common denominators. You keep the denominator, add the numerator, or subtract the numerators, okay? So I'm just doing that in reverse, all right? That's legal in most states, right? Okay? What does that become?
So 1.
1. If I could get the pen to write. Minus, and what's that? Cosine squared theta. And what's 1 minus cosine squared? And that's sine squared theta. That, I think, may be just a little easier, but they're both pretty easy. So you're usually more than one way to skin cats if you don't like cats, you know, but, you know, if you like them, don't go around doing that, okay? So, yeah, they did it the way, well, they didn't quite do it the way either one of these ways, they just deviated a little bit from the first one. So let's see how they did it. Any questions before I delete this? Okay. So let me erase my scratch. How did they do? They started the same way we did, except strangely, okay. Oh my goodness. They wrote that secant squared theta was tangent squared theta plus 1, then subtracted 1 from it and came up with tangent squared theta that way. I did it just thinking, I thought that same thing, but then subtracted one for both sides, and you got it. And I think that's probably what you did, okay? But anyway, they came up with the same, well, not yet. They're trying to get to the same thing. The next step, they're at the same thing. Okay, now whereas I went to sine, in terms of sines and cosines, they are saying that tangent squared theta times 1 over cosine squared, it's not 1 over secant squared theta, which is cosine squared theta. Okay, and now they write tangent in terms of sines and cosine, and that gives you the cosine squared thetas disappear, and you're left with sine squared theta, which is the right-hand side. I think they went around their elbow to get to their ear, so, but it's another perfectly good way of doing it. Like I said, many ways to get there. All right, and that's equal to sine squared theta, which is the right-hand side. Notice that you verify the identity by starting with the left-hand side, more complicated side, and using fundamental trigonometric identities to simplify it until you get to the right side, to the other side. Okay. Now, later they'll say, but it's okay to do it the other way. Okay. There is a checkpoint there, and please do that, especially if you need to review what we just did. Let's see. Whoa! Guess what? This whole section, which contains 7 examples, they do uno, 1. Okay? So let's do the rest of them, at least until we run out of time, and you'll keep me on top of that, right? Okay. So here's one. They did the simplest one for you on the PowerPoint, and then left all the more complicated ones for you to figure out on your own. So here we have a 2 secant squared, is it theta? No, alpha. Okay, call it alpha. Okay. They're claiming, but I'm going to put the question mark there, that that's the same as 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. Okay? Now, what would be your approach? What would be your first gut reaction to that? And don't say throw up. Never. Okay. How would you proceed?
If you use the right side,
Okay.
and then a common denominator.
Fantastic.
Could you
Okay.
find the Pythagorean identity
Right.
that way?
Yeah. Okay. Now, they've got you thoroughly indoctrinated, don't they? I like to do both sides. This side you're right. The right-hand side is the more complicated side. But on the left-hand side, I can simplify that one step, getting in terms of cosine. So this will be the same as 2 over cosine squared theta. That may, or alpha. That may not be helpful, but at least I got it in simpler things. Okay? Now, on this side, as you said, we need least common denominator. And what denominator will that be? You multiply the 2 together. So this will be, you got started with a 1 over 1 minus sine alpha. And you're going to multiply it by 1 plus sine alpha. But if you multiply the denominator by that, what had you better do? Multiply the numerator by 1 plus sine alpha as well. Okay? Over here, you had a 1 over 1 plus sine alpha. And to get the least common denominator, you have to multiply it by 1 minus sine alpha. But if you multiply the denominator by that, you got to also multiply the numerator by that as well. Okay. Now, not going to even mess with writing down the left-hand side. It's okay. All right. Now that you got this common denominators, let's fiddle with your numerators. Here you have a 1 plus sine alpha plus 1 minus sine alpha. That's in your numerator. And what's in your denominator? Yeah, I think you said it at the very beginning.
It would just be, it would be 1 plus sine squared.
1 minus sine squared. Okay, because the sum times the difference of the same two entities gives the difference of their squares. Difference of their squares. Sums of squares you can never factor. Differences you can. Okay? Now, what do you notice in that numerator? Say again?
You could add the 1s.
Add the 1s, and that gives you, I'll put it here. Now you'd be doing such high-level math today, but 1 plus 1 is 2, okay? And how about the rest of the numerator?
The sine subtract.
Yeah, sine minus sine is 0. Okay? So you got 2 over, and what's 1 minus sine squared? Cosine squared theta, or alpha. And that's exactly what your left-hand side became. So that's why, see, for them, they got to do one more step to get that back to here. If you do that step up here, then yeah, you see they're the same. Okay? And I'm lazy, so I do it as short as possible. All right, good deal. Does that make sense? Okay? We just verified it. They did it slightly differently, but they both work. There is a checkpoint. Highly recommend you do that one. Okay? Ready for example 3? Okay, let's erase the ink and do example 3. Verify this identity. Tangent squared, this time it's x, plus 1 times cosine squared x minus 1. Supposedly, we don't know, they claim it's equal to minus tangent squared x. Okay? What would you do first?
Find the Pythagorean identity.
Okay, and what would that give you?
The secant squared for the tangent.
Okay, the 1 plus tangent squared is secant squared. Oh, I can't write. X. Okay. For some reason, my pen was wanting to write a sign. So let me. Okay, that's the secant squared x. Say again?
The next one will be sine squared x.
Just about, but not quite. Negative sine squared x. You're absolutely right. Okay?
So then you could just make the secant of 1 over cosine squared.
That's 1 over cosine squared x. That gives you negative tangent squared x. So, you could have, and I probably would have, let off on the right-hand side. Since I was messing with the left-hand side, I'm going to mess with the right-hand side a little bit, get it in terms of sines and cosines. And you have that as minus sine squared over cosine squared. And then at this step, I have them be the same. So they're exactly equivalent, and they're doing the same thing, just whether you take it on one line or use another line on a piece of paper, which they're cheap, but I'm still stingy. Okay, so those check. There is another checkpoint there. Please take a look at that. Now, they do show another way that you can check to see if your identities really are identities. If you have a graphing calculator and you know how to do this, then enter one side as a function, as your y1 say, then do y2 as the other side, and then say plot or graph or whatever your command is there. And you'll see the first one map out, and then if you look real carefully, if they are identities, the second one will map right on top of it, but you can't see it unless you're really watching and you see the cursor doing it, because it'll look the same.
So the parallel
universes almost. Yeah, right, yeah. They would be exactly the same thing. And they show that here, but you can't really see it because it's all written on the same line. Okay, so let's move to example 4. All right, to erase?
Yep.
Okay, I did anyway, okay. Verify each of these identities. There's 2 of them here. The first one is tan x cosecant x, they claim is secant x. Tan x cosecant x, they claim that that's secant x. Now, what would you do on this one?
Just
Second?
you could just take the tangent, put it sine over cosine.
Absolutely. Let's get everything's in sines and cosine. So that's sine x over cosine x times, what's cosecant in terms of sine and cosine? 1 over sine x. Ah, this is looking good. And what happens? They disappear,
And then you have 1 over cosine,
which is secant x. Perfect. Done. That was pretty simple. Let's do the B one on the same line. Ooh, it may not be as simple, but let's try. Tangent x plus cotangent x, they claim, is equal to secant x times cosecant x. What would you do on this one?
So it would be easier.
Second?
So I'm trying to figure out what side would be easier.
Okay. Here's my suggestion. Do them both. Just start working on both sides. Just don't cross the equal sign. So what would you do on the left-hand side?
Put it in terms of sine.
Yes. Okay. Sine x. What is tan x?
Sine over cosine.
Over cosine x. Plus, and what's cotangent x? Cosine x over sine x. Okay. What is secant x? 1 over cosine x. And what's cosecant x? Perfect. Okay. Now, let's fiddle with the left-hand side. Okay. If you've ever taken violin lessons, so never. Okay. What would that be? What would you do there? Common denominator. What would that be? The product of the 2. So there's a sine x times cosine x. You started with sine x, and then you multiplied the denominator by sine x, and now you got a sine squared x, right? And on the second one, you already had a sine x and a cosine x above it, and you multiply by a cosine x. If you multiply the denominator by cosine x, you must multiply the numerator by that too, so that makes cosine squared x, doesn't it?
So it'd be 1 over.
That's 1 over sine x cosine x, which is exactly what you've got there. Right? What they would have done was just do the left-hand side and get to this step and say, ah, that's secant x times cosecant x. But since we had already done that up there, we're already there. How are we doing?
Got 7 minutes.
7 minutes. That gives us plenty of time, doesn't it? All right. So that gives us there is a checkpoint after example 4. All right. There's a little blurb at the top of the page that I've already kind of introduced you to. This is page 358. And let me go on and get that done. See, this blurb certainly should have been on the PowerPoint. But no, I just did one example and left. If you ever have a form like this, and we ran into one already, and I made this suggestion, 1 over 1 minus cosine x. And this still would have been true if that had been a plus cosine x. What is one way to simplify that? It's not an identity, but if either side of an identity, one way to simplify it.
You make it a cosine as secant.
I never go that way. I always go from the bigger ones to the sine and cosine. I don't want to say never, but most of the time don't go the other way. Okay? But remember, this is
so it's a quotient, so
yeah.
could you write it as 1 minus 1 over cosine?
Okay. Nah. Okay,
Split never mind.
yeah. Making up new rules. Okay. Remember, we had one like it earlier. I said multiply by its conjugate. Remember? What's the conjugate of that?
Multiply on 1 plus.
Yes, 1 plus cosine x. But of course, if you do that, you got to multiply the numerator with 1 plus cosine x too. I can't write. Okay. And what does that denominator become? In other words, why did you do that? 1 minus cosine squared x. And you got 1 plus cosine x on the top. But what's 1 minus cosine squared x?
Negative sine.
Not negative. That is sine x, okay? 1 plus cosine x over sine squared x, right? Pythagorean identity. Okay. Now you've got a monomial in the denominator, and you can play around with that. You can say this is 1 over sine squared x plus cosine. Yeah, you can do lots of things with it. Or leave it just like that. That's fine too. But then you could write that and get rid of make that a cosecant x, and so cosecant squared x. The other one would be a cotangent x times cosecant x. So, yeah, you could get it out of the denominator. Okay? Now, and they make a really dumb, but it's true. Okay, let's carry that on out. They're going to do it, okay? And this would then be cosine x over sine x times 1 over sine x. I did it again, okay? And that would be cosecant squared x plus cotangent x cosecant x. I said it, I didn't write it. Okay. And then they make the almost ridiculous sounding statement that this is a simplified form of that. I say, you've got to be kidding me. That looks more complicated than that. It's got squares in it, it's got cofunctions in it, it's got all sorts of things. But what they mean is, this one has a denominator, that one doesn't. So that's why they say that's simpler. Okay. You can argue with that if you want to. So this next one, example 5, is also found at larsonprecalculus.com. So you can either this one or one very similar to it. It's asking you to verify an identity, which is what we've been doing all along. Okay. But this one's a little more maybe involved or something. Let's see what we got here. Here we have a secant x plus a tangent x. And the question is that equal to a cosine x over a 1 minus sine x? Okay. What would be your approach?
Simplify both sides.
I certainly would too. I like the way you're thinking, okay? All right. Well, how does the left-hand side simplify? 1 over cosine x plus sine x over cosine x. Okay? The right-hand side, what would you do? Multiply the denominator by its conjugate. What is the conjugate of 1 minus sine x? 1 plus sine x. Okay? But if you multiply the denominator by that, you also got to multiply the numerator by 1 plus sine x. Okay? Now, okay, I did it up there. Let me bring down and see what we've got here. What is your new denominator? Minus sine squared x, perfect. And your new numerator, I would say let's leave it just like it is. Cosine x times 1 plus sine x. Sometimes it's good to multiply through, sometimes I think we can get by without it. Now here's why I suggest we not. Look over, you can look, remember, you can look across the equal sign, you just can't cross it. This reminds me of a story of two of my nieces. My older brother and his wife had 2 girls fairly close to age together. For some reason, Renee was convinced that the more they competed, the more they pushed each other to do better. So she pushed them to compete with each other all the time. They really turned out to be obnoxious kids and obnoxious adults almost, you know, when they're around each other. Individually, they're both fine. When you get them in the same room, it's miserable. Okay? But never mind, we won't go there. Okay, so when they go on long trips, it was always, she's on my side of the seat, you know, or this, that, and the other, just fussing the whole time. So my brother started putting suitcases or coolers or anything in between them so they couldn't possibly get on the other side of the seat, thinking he had solved the problem. And they were driving along on some long trip one time, and then out of the back seat, she's looking out of my window. So that's okay. You can look across that equal sign, you just can't cross that equal sign and get in the other space. It's okay to look across and look out of the other window. Okay? So I looked across here, and what did I see? Yeah, you get a 1 plus sine x. So why mess with that? Leave it as a 1 plus x, sine x. Okay? So in fact, let's write it that way. 1 plus sine x over cosine x. Got the least common denominator. I mean, they are common denominators, put the numerator over that. And then the question is, what is this? Well, I see the cosine x up here, and there's that 1 plus sine x that I don't want to mess with because that's what I got on the other side. But what does that denominator give me? Yeah. What is that?
Oh, it's cosine.
That's cosine squared x. And now look at what you can do. You can divide out this cosine with one of those, and guess what we got?
We have the 1 plus sin x over cosine.
Which is exactly the left-hand side. Yes. Okay. Got it. Make sense? All right.
We're out of time.
Yeah, that's what I was guessing. So that was example 5. We'll begin next time with example 6. And that is, and if I don't remember this, see if you can remind me. There aren't any more slides on this side, so we'll only get started on 5.3, and we'll come back and do it. No reason to pull up 5.2, even though we're still in 5.2, because there's no slides in there. So 2 more of those to do. Homework exercises here. This is for you, but also anyone that might listen to this. Any of the odds 9 through 17, they're all at Calc Chat, 9's at Calc View. Any of the odds 19 to 23, they're all at Calc Chat. 21's at Calc View. Any of the odds 25 to 29, they're all at Calc Chat. 27's at Calc View. Any of the odds 31 to 35, they're all at Calc Chat. 33's at Calc View. Now we haven't done any like the next group, but I'm not sure the examples are going to give us any of those either. But you can stop there if you want to, and we'll pick up the rest of it later. All right, good deal. Thanks for coming. It was a lot better than talking to myself, I guarantee. So I appreciate your making the effort.
I'll see you Tuesday.
We'll see you Tuesday.